Did you know that 1 in 10 people will be diagnosed with skin cancer at some point in their lives, and the only current method of diagnosis, invasive biopsy, is more dangerous and inefficient than potential answers out there? Here's how a non-invasive optical biopsy with harmless laser light could theoretically be developed. Now for this, we're going to need to measure the fluorescence and lifetime of 2 very important molecules, NADH and FMN, or flavonomononucleotide. So, let's jump in. As you can see, there's a significant lifetime difference between folded versus extended NADH. Folded also leans closer towards glycolysis, which the Warburg effect tells us means it's more likely to be cancerous. This summer, I worked to create a laser microscope in order to quantify the changes in NADH and FMN, the metabolic and structural changes. And here's the logic behind it. 2-photon excitation is when you shoot 2 photons at the same space instead of 1. It doubles the wavelength but acts as 1, which makes it more beneficial for this project than single photon excitation, because single photon would fall under the parameters of UV light, which would be dangerous and skew our results, while doubling the wavelength makes it fall into infrared, which is much safer for imaging. The light moves through a pulsed laser and goes up through a series of lenses and mirrors where it raster scans across the sample and goes back down reflected by a dichroic to the detector, which shows us our images. The images are on a color scale according to intensity, 400 to 1400 picoseconds. Each pixel contains valuable data that we will now transform into a more viewable format. Information from each pixel is put into a sine and cosine transform, which produces a phasor plot. This essentially functions as a lifetime graph while also covering the extended to folded ratio discussed earlier. I drew up a small model of a phasor plot so I can efficiently show you its use and how to read it. Each individual pixel on this makeshift phasor plot results from data from a pixel of the actual image. This dashed line is where NADH should fall given its components. As the graph moves further towards the right, it falls towards NADH's more folded state, which means it's more associated with cancer. However, as it moves back towards the left, it is where NADH falls into its extended state. So by looking at this graph, we can essentially tell its extended folded or free to bound ratio, and by that determine whether the cell is cancerous or not. Another component of the phasor plot is the tail leading towards the origin. We initially thought this was unmodulated light, however upon further inspection it's likely collagen fluorescence. We have switched to second harmonic generation imaging and added a new detector for collagen, and we will take collagen data into account in our next experiment. Overall, in measuring the lifetime of these molecules through their fluorescence, we should be able to monitor the metabolic and structural changes in the skin, therefore being able to catch cancer before it fully visually develops.